So first, thank you to the organizers of this super symposium, Katrin Schäfer, Martin Frieder, I think Philipp Mitterk has also done work, and all others that contributed. So my talk is about human biocultural evolution and its relationship to cranial capacities. What does it have to do with the brain? What happened in the last million years? At least in the last 2 million years, we cannot understand what happens in human evolution if we don't look at the culture as well. So it's not only the biology, it's also the culture that was tremendously changed. And there's this paper that I published in April 23. You can download it for free on my webpage, where we looked into just the fossil record, as it was done before several times in other works. What we did was we looked at the cranial capacity in cubic centimeters. That's the cc over there in milliliter, the cranial capacity in milliliters, in the fossil record of 193 hominin fossils. So going back from 7 million years to the last 10,000 years. And we tried to find the most modern or recent estimates of cranial capacity. You know that some of these fossils are fragmentary, so they have to be reconstructed, and there are different reconstructions. So we gave a focus on the latest news, as well as for the dating, because dating is also ambiguous. The dating that you have here is in million years. What we also did was we excluded all specimens before the age of 11, because with the age of 11, we reach on average 95% of the adult brain size. And so we only compared these and not the young individuals. That is what came out, and you might have seen such graphs already before. The news is here, the broken stick or segmented regression. And we didn't entertain long discussions about the taxonomic affiliation of these specimens. You know that there is a lot of ambiguity also in our science about what belongs where and what taxon is it now. So this is a very simple grouping here that we have. We have pre-Homo. Yeah, it's not too complicated to say this is pre-Homo. Then we have early to mid-Pleistocene Homo. It's done by the time. And then we have late Homo. So very simple distinguishing. And for instance, Neanderthals and modern humans are all together in the late Homo group. So we don't want to discuss what is what. But we just looked at the cranial capacity and time, and you have the last 7 million years here. And as you see, there's two things that are very, that spring to your eye. Or what did Fred always say? It must hit you between your eyes, right? And what hits you between your eyes, even if there would be no lines here, is that you see there's something going like that, and then there's something going on like that, more steep and even steeper here. So what we did was we applied segmented regression. This was done the first time to this kind of data. And what this segmented regression can do for you is, if you tell it, or I see 3 segments, then it finds the exact breakpoints. So it fits 3 regressions. The first one is here, and it shows you where the exact breakpoint is, and it gives you a standard error for that. And what we see is that not much is happening in the first 5 million years. From 7 million to 2 million, there's a slight increase in cranial capacity, which we use, of course, as a proxy for cognitive abilities. I mean, we don't have anything else to talk about creatures that lived 3, 4, 5, 6 million years ago than cranial capacity, okay? But there's not much happening here. Very slight increase until 2 million. And then there are even some, I will talk about that in a minute, some of these organisms that continue that pathway. But what we see then at 2.1 million years, something happens. 2.1 million years, the slope is much steeper here. Yeah? And that's coinciding with the early to mid-Pleistocene Homo. Yeah? And you see a dramatic increase of the cranial capacity from 2.1 million onwards. And then you see another breakpoint, and that's what this segmented regression can do for you. It tells you where the other breakpoint is, and that is at roughly 110,000 years, yeah, plus minus. There's a standard error associated with it. And then you see the third part of the regression, which is even steeper, yeah, in the last 110,000 years. And so we have to think, what does it mean? And do we find any correlates in the archaeological record that would somehow fit to these physical data that we have here? Just to finish the actual data part here, what you see is that we have the pre-Homo with a mean of roughly half a liter, yeah, of cranial capacity. The early to mid-Pleistocene Homo, roughly a liter. And the late Homo, roughly 1.5 liters, let's say it like that. So there are really huge differences, and they are significant if you do a test. What is also surprising, I find, is the correlation coefficient between the cranial capacity and the age, the dating. This coefficient is 0.8, and that means that we can explain 70% of cranial capacity just when we know when this creature lived. That it was astonishing. And then you have here the cranial capacity by chronological age segmented regression, the exact dates, so it's 2.1 million years and 113,000 years plus minus these standard errors. If you look at the graph, you see that there is not even a real overlap between pre-Homo and early to mid-Pleistocene Homo. Yeah? In the distribution, there is an overlap, of course, between early mid-Pleistocene to late Homo, but the boxes which represent the middle 50% of the distribution don't even touch. I go back to this graph, which gives a bit more information about the taxa, because I said we just handle 3 groups, but for more detail, we of course looked also into narrower groups. So you see 8 groups here. There are Australopithecines, Paranthropines, Habilines, Erectines, and so on. And I just want to point your interest to this. It works, yeah. These are the Paranthropines, yeah, and they just extend what happened before, yeah, from 7 million to 2 million, and then we have this change. But they are continuing what happened so far. Yeah, they're just going along the old path. So not much change in cranial capacity, but as Markus just referred to, a dramatic change in mastication. So that is interesting. At the same time, 2 different lineages invest in different strategies. The one into massive mastication apparatuses and small brains. You see that over here, die out, around 1.2 million. The other, small faces, smaller mastication apparatuses, but bigger brains, we're still here. The other thing probably that would come up in the questions, so I do it in advance already here, is what about Homo naledi? What about Homo floresiensis? They are here, just plotted for interest. They are not considered in the computations that we did, because Homo floresiensis is a kind of insular dwarfism, and Homo naledi is a very primitive hominin, still living at a later time, 200, 300,000 years ago. There's no tool industry, still a primitive adaptations, so we don't consider both of them as having significantly influenced our evolution to Homo sapiens as we are today. So they are not considered in this data, but just for curiosity, so that you know where they are along the old pathway, right? That we saw before. So our problem, I hope this works, yeah, is how can we connect the technological innovations, such as advanced tools and so on, which are far beyond anything that animals can produce. Yeah? I know there's this discussion about what can animals do, and they are using tools and so on, but we are talking just about things that no animal has ever done, yeah? Like a Schöllian hand axe or using fire. How does this connect to cranial capacity and intellectual capabilities? What we see anyway is that the number and diversity of objects that are coming from the abiotic domain are progressively increasing over the last million years. And so there are the questions, since when can we recognize the influence of cognitive abilities on human survival strategies that go beyond those of other animals? And was this a continuous process, or do we consider or recognize leaps in this process? And can we diagnose a concordance between brain evolution and cultural development? There's a problem associated with it because cranial capacity data, which we use as a proxy for cognitive abilities, and data are metric, and dating are metric data. Yeah, so they are expressed in milliliters and years. No problem with that. The problem comes when we go to the cultural complexity. So we do not have any measure, any real good comparable measure for cultural complexity. So how would we compare an Australian index with an ivory figurine from the Upper Paleolithic, yeah, in terms of complexity? How could we give it a grade or whatever? Yeah? So it's very qualitative what we are doing here, and that's a problem in this comparison. And the other problem is that life and technology are usually growing exponentially if they are successful. Yeah? And to find the beginning of an exponential growth is very hard. I mean, we have our problems to find things anyway in the archaeological record, in the fossil record. It's a very big chance if we find anything, but that we find it when it first appears, let's say a new technology starts, yeah, and then grows exponentially, that we find it at the very beginning and so know when it really started is also very unlikely. So these are the problems associated with what we want to do here. But what we see is, for instance, a Schöllian index. This is something that probably nobody in this room can do. Probably there are some experimental archaeologists here. They can do that. But this is already so complicated that we cannot do it. If we crash with an airplane somewhere in the Andes, we cannot do that. We can do all the one tools, but not that. That's already too complicated. And we have that since roughly 2 million years. Fire, yeah. Also difficult to say when it started, goes back 1 million years, probably more. The revolution in the mid-Paleolithic, yeah, with a totally different core preparation technique that was used by the Neanderthals, the Valois technique, and so on. So a next technical revolution, distance weapons, yeah, 300,000-year-old spears that were found to be, very usable. Also in modern times, they used spear throwers to test them, and they say, yeah, they are fantastic spears. Eagle claws used as decoration. Then we have these okapis with probably symbolic contents. Yeah. So the suspicion is that these lines mean something. We have a composite figurine between man and animal. So there's already a lot of inspiration behind it to do it. Music instruments, we have other symbolic figurines. We have cave paintings and so on. So we see the complexity is increasing, but it's very hard to put that into numbers. Yeah? So how do we evaluate this painting or this figurine in comparison to Middle Stone Age revolution? Yeah, very difficult. But we were putting together this graph, which is just a schematic graph that should indicate something which is happening in human evolution. I mean, here's the start of life. We don't have to consider that, but here we are at 7 million. Then we have Ardipithecus 5 million, Lucy, which was just celebrated this week or last week, 50 years of discovery of Lucy. So Australopithecus, 3 million years, Homo erectus, first people going out of Africa into Eurasia. We have all these amazing stone tools and other artifacts and the okapis. And we are here now in the digital transformation, right? What we see is that the green one, the green part here is the random-driven organic domain. So that's what's happening to every life form on this planet and happened since the last billion years, okay? And we consider it random driven, and it's nature, the selection, and all this kind of things. Okay, and then we have this blue part here, and that I would consider the mind-driven part, yeah? Where we use our intellectual capabilities to, to find better strategies for survival and change by time also our environment. And we are including more and more abiotic means into our life. I mean, look at this, where you are sitting today. So this is growing. The mind-driven part is growing for us humans. Of course, we are influencing a lot of animals and plants too. And the green part is going in the background. Yeah? That's just schematic. We cannot really measure that, but it's something to keep in mind. And if we go back to our graph and we say, okay, we have here the first breakpoint. So what is associated with it? If we look into the fossil record, archaeological record, I would say 2.1 million. It can be, we can talk about 1.9, 2.3 million. Yeah, there is a standard area associated, but around that time, we have the proliferation of the genus Homo. It's not the onset of the genus Homo. That was probably 2.8, 2.5 million years ago, but the proliferation of Homo, yeah? And the increasing number of apes from the abiotic domain that we see associated with it, and it was leaving Africa. That's around that time. What is associated with the second? It's a symbolic thinking, the abstract thinking, the symbolic behavior that we see coming up around that time. We can discuss 100,000, 70,000, 110,000, what you want, but around that time, we see more ornaments, we see more symbolic representation. The okapis that I showed you is 73,000 years old, I think, from South Africa. So that's happening in the second breakpoint. And now we are here at the third breakpoint, even steeper increase. And the question is, are we at the border of intentional evolution? Because we can take evolution now in our own hands. What we are doing currently is we are outsourcing our brain functions. So memory, computations, hardly anyone can remember anything. We have Google to look at, and if we computations, forget it. For the easiest computation. In the supermarket, we use already our calculator. We have created artificial intelligence, particularly in the last few years, became very popular. So we are also outsourcing thinking and making decisions. That is on its way. It's not there yet, but it's on its way. We have these social medias and networking, which is a very interesting experiment because our brains are the most complex structures in our solar system, and we are connecting billions of them into a new superstructure now. Doesn't always work nicely, but it's a funny experiment, what we're doing here. And we are using genetic engineering, and we can directly interfere with the proteome, the genome, and so on. So the questions, for instance, are, how would we account in our plot, in our graph, about brain size? How would we account there for this artificial intelligence and machine power that we are using. Actually, we would have to include it, yeah? Because we enlarged our brains significantly now with these machines. But we don't have the means at the moment to how we would include that into the graph, but it certainly would make the slope steeper. How could we reconcile our lives in the analog and the virtual world, which is at the moment a problem, particularly for young people? Or how do we decide about desirable traits of humans, which we would have to do on our own? If we recapitulate the history of the last million years, I think that we can very easily recognize two trends in our biocultural evolution. First, employing sophisticated cognitive strategies and the utilization of abiotic resources became the prevailing principle. And second, this development accelerates over time. So the next logical step would be that abiotic creatures, which are equipped with artificial intelligence, would reproduce independently. And that's actually something that already happens. This company here in Colombia has the goal to produce machines that produce machines. So independent, then machines are produced without the interference of humans. Okay, that's the next step. You know probably this, not a person, is Sophia, which is recognized as a citizen since 2017 in Saudi Arabia. It's a robot. So we are a bit on the way already. And our biocultural evolution is shifting from this randomly driven natural process to a mind-driven transformation guided by us, by humans. But this is a type of responsibility which we are not really ready for. And if you look into the documents of the large agencies like EU, US, OECD, there's not even one mentioning about any biological effects that the digital transformation might have. There's never any topic, but we should probably consider it. It's time for a discussion now. I'm very grateful to all these people who helped me with this work. And that was the talk for today. Thank you.